Okay, so I guess the first thing I want to say is there are a couple of questions from Piazza. I think it should be really helpful for the homework, and I would encourage you to take a look. It's about problem 3 and problem 4 on the Piazza forum. I believe this is lecture 21, and as we mentioned, we're going to look into the branching process. So you can think about this as a special kind of a Markov chain where the state space here is it's infinite, and it's the space in this case is actually the non-negative integers. So we will be looking at the branching process maybe for the next 3 lectures. But I think after the Friday's lecture, you should be able to do the last problem on your homework set. So okay, so maybe first let me give a little bit of a description of this this model. So for the branching process, let's see, let me cut the board in half. Right. So we can think about this as so this is the population. The population of individuals that reproduce at each time step n. Reproduce at each time, or sometimes we'll also call this level. And when I draw the diagram, it will be clear. Each time or level n. Right? And over here, in general, we're going to use the xn. This is going to be the number of individuals at time n. That's time or level n. Right? So that's just the notation here. And then now I'm going to just simply describe like how. And over here, furthermore, maybe I'll just say this first. So each individual will produce a random number of offspring. And then after reproducing them, an individual dies. Or you can think about just one thing will branch into a random number of other things. And of course, the number here could also be 0. So that just means that individual just dies off. So each individual produces a random number of offspring. And okay. And let's say n dies afterwards. Okay, so essentially you can think about okay, maybe I'll draw a diagram later and it will be clear. And then there's also some assumptions about the reproduction process. So these are the assumptions. Okay, maybe it's helpful to draw for me too. Okay, I'll draw it next. So assumptions. So 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 the idea is that each individual will have so essentially the way that each individual produce the offspring, they follow some IID discrete random variable. So these are all IID. Okay, so I'll just write each individual produces offsprings with the same probability distribution And so this just means that, okay. So maybe I'll say another way to say this is we have a sequence, let's just call them P0, P1, P2, etc. Right? So this is a sequence of non-negative integers. We have non-negative which are non-negative. And of course, being a probability distribution, we would want a sum of I goes from 0 to infinity of pi. They're going to be equal to 1. So we have the sequence of non-inverse, that sum of 1. And each individual has k children with probability pk. Okay. Each will have k children with probability pk. Right? Pk is one of the elements from our sequence, P0. So you can think about the number of children could be 0, 1, 2, 3, and etc. Right? Could be any non-negative integer. And the second one is, of course, individuals, they reproduce independently. Right? So this says they have the same distribution. And then the second one is also just that they're in fact IID. Right? So individuals reproduce independently. Right? So these are the two main assumptions. And maybe let's introduce some notation. Okay. Notation. So let's use the let's use z sub I of n denotes the number of offspring or children, produced by the ith individual at the time or level n, right? So you can think about these zins, they're just IID discrete random variables, right? They're all the same. And of course, sometimes so if we're just going to be looking at this offspring distribution, sometimes I'll also simply write this as z if the I and n here, they're not important, right? So, okay, if I and n are not important for our argument, we will simply just write as z. Simply write as z instead of with indices, which you can later on I'll show. See, okay, and oops. Right, and then for example, okay, maybe I'll give example. So for example, we know that probability p that z is equal to k, this is equal to 1. pk, right? That's just like one of the examples where we use the simplified notation. Of course, in this case, I and a are not important; they're all IID. Okay. Okay. Maybe also write for k, let's say it's between 0 and infinity. Right. Okay, maybe integers. For k is equal to 0, 1, 2, etc. Right? Yeah.
So you see that produces offspring with the same probability distribution.
Yes.
Like P0, P1, P2.
Yes.
Right. So this probability distribution is not based on the time.
It's fixed. It doesn't based on it doesn't depend on the time. Yes, you can think about it's a time homogeneous Markov chain. So the way like the probability that they reproduce it's independent of time. It's something that you fix at the beginning. So you fix these P0, P1, P2, and then you see how the population grows or decays, I guess. Okay, and maybe we can draw the diagram. So why is this called a branching process? Why is this a branching? Okay, so now we can just start with an example with a realization. So now, for example, this is our time 0, and let's just assume that the number of individuals in our population at time 0 is just 1, right? And in this case, and we can also ask, and now let's say suppose this individual here, right? It would produce several offspring, and in this case, let's say it produces 3 offspring, 1, 2, 3. So in a single time step. Right? So in the picture here, it just means z. Let's say it will say z01 over here is 3. Right? So that means in the 0th time step, and okay, maybe for the notation, maybe I'll just write that small. Yeah. So at time 1, so right, so it produces 3 offspring, and in this case, let's say this means x1 now is 3, right? So remember the x just counts the number of individuals in total, and in this case here, let's say this one splits into 2 in the next time step, and this one just doesn't produce anything, and this one produces 3. Right? And then you can imagine the process would go on and on, and there would also be a time step where like everything inside this entire time step, they don't produce anything, so everything just dies off. Right? And okay, so let me draw this one a little longer. So in this case, x2 is going to be what? x2 is 5, right? Exactly. And now what is z2 of 1, z2 of 2, and z2 of 3? What are these 3 quantities? Yeah, exactly. Yeah. 203. Because 201 is the number of offspring to time 2 of the first individual, which is over here, and this is the second individual. This corresponds to z22, and this corresponds to z23. Okay, and of course, then we also have the general formula. So xn is equal to the summation of I goes from 1 to xn minus 1 of z n I. So maybe I'll highlight this formula. Right. So essentially, this formula just says if we look at the number of individuals in the nth step, right, we just have to add up all the number of offsprings produced by the each of the individual from the previous time step, right? In the previous time, the number of individual is xn minus 1. Okay, so let me take a pause. Any questions? Yeah.
Are you just assuming that every person like is it
Yes, yeah. So you, yeah, and I mean, it could also be 0, right? It just like dies off, just like this case here. Yeah. Oh no, yeah. There's no, it's just like each individual and they reproduce independently, just like the diagram here. Yeah, that's a good question. Okay. Any other questions? Okay. And so of course, then this is, so we can see that the sequence xn here is a Markov chain. But in this case, the transition probability is very hard to write down. So the transition probability xn is a Markov chain, but the transition probability is hard to write down. Maybe I should add is in general. Of course, you can choose the PIs in some special way that in general, it could be easy, right? So for example, let's just say PK of J. So we go from K individual to J individual. This would imply that this is the probability that xn here is J, given that xn minus 1 is K, right? And just using that formula over there, this just means the probability that we have this is Z n. Over here we have 1 plus Zn of 2 plus all the way to Z. In this case here, we know that in the previous time step, there are in total K individuals. So the index here would go to K of time n, right? So this sum here has to be equal to J, given that xn minus 1 is K, right? This is just this formula over there. And then we use the fact that the xn minus 1 is K. But in general, this is the sum of IID random variables, right? Sum of IID random variables. And if we have, in general, the sum of IID random variables, its probability mass function, or in general PDF or anything, these are really hard to compute in probability theory. I mean, of course, there are some special cases, right? For example, sum of Bernoulli is a binomial, but in general, these are very hard to compute. Okay, so now we can look at, there are some other ways to analyze the model. And okay, so now let's also make some other assumptions, right? So we now, from now on, we now assume that P of 0 is between the 0 and 1. Recall that P0 here is where P0 is just the probability that they reproduce no children. Okay, so they just die off. Okay, the reason is because we want to assume this is you can think about if P0 is 0, then the population will just always grows. And if P0 is 1, then there just will be no like reproduction because no ones can reproduce. Right. And so we're gonna this is some of the natural assumption. And then so with this assumption, then we can note the following. Right. We can note that so what's PK of 0? I'll ask you guys. What is this probability here? Where we go from K individual to no individual in the next time step. Sorry, what? Yeah, exactly, right? So in the previous time step, we have K individuals. And in the next time step, we have no individual. That must mean like each one of these has no children. So that's like, and because they're all independent, so it's just P0 raised to the kth power, right? Which is some positive quantity. Okay. So now I'm going to write down the sentence and I'll ask you why. So this implies that for any K that is greater than equal to 1, right? Inside our state space, for any K is greater than 1, K is transient. K is a transient state. 0 is the only recurrent state. For this Markov chain. And okay, not only 0 is recurrent, it's actually stronger. It is actually absorbing, right? Actually absorbing. This just means if our Markov chain gets to 0, right? If xn is equal to 0 for at some time n, then xn plus 1, xn plus 2, these will all be 0. Right? So maybe now I'll ask you guys, why does this statement implies that for any positive k, let's say 1, 2, 3, they're all transient states for this Markov chain? Sorry, can you say that again? Which state they cannot leave? Right. So I guess we have 3 definitions, right, for the transient or recurrent equivalent. And I would say in this case, the easiest one to use is the one with the heading time, with the t. Right? So you can think about if the Markov chain starts at k, and yeah, sorry. Yeah.
Based on the tree.
Yeah.
It will not be some vertex that is causing the state, right? If the individuals will not to make child, then it will be a absorbing state, is that right? And if the individuals will make the child,
yeah,
it will not to go down to another step, so it will be a transient.
Well, these are not the states, right? These are the states, the 1, 3, and 5. Right. So our Markov chain is the sequence of xn, right? So for example, in the first case, we are at the state 1. In the next time step, we go to 3. And in the next step, we go to 5. Right. So so these diagrams here just help us to analyze this Markov chain. Oh, yeah, sure. Exactly, and why? Yes, the probability of reaching 0 is non-zero, right? But why does it imply they're transient?
The last stage, the crucible stage is the state.
What? Sorry, what is the? When you say the last state? Yeah.
The state is finite, and it will finish in the n state. So fall from 1 to the n minus 1, the state is all the test state, is that right? Because they must will go to another state.
Well, let's see. So I guess in this case, they're transient essentially because they get to 0 and then they can never come back, right? You can think, but that's the intuition. Yeah. Or do you have anything to that? Yeah.
So the heading time to 0 is going to be finite. The probability is always not 0. And once you're at 0, you have to have at least one individual making offspring, so which is stated at 0.
Exactly. Yeah. Right. Yeah. Exactly. So in this case, you can, yeah, that's essentially that's essentially the idea. Yeah. So it's because okay, I'll just write down this. It's because this is because with positive probability, we would have T of k is equal to infinite, right? So this means, and then, okay, the reason that with positive probability Tk will be infinite is because with the positive probability we can go to 0, and once we go to 0, we can never come back to k, right? Because since I'll just write the probability p that Tk is going to be infinite, given that x0, given that we start at well, in this case, sure, we can start at k. Just this is not right. So now this is always going to be greater than or equal to p k 0, right, which is positive from our previous calculation. And maybe I'll explain a little bit about this inequality here. Well, this is because imagine if we started with k individual, and in this one special case where all the k individual doesn't reproduce, that means our Markov can go to 0 in the next time step. Right? But once we get to 0, then there's no way for us to come back to k, because 0 is absorbing. So we'll just stay at 0. So right here in particular, the tk just has to be infinity, right? So this just means this probability here is strictly positive. That must mean that by definition, that just implies it's k is transient. It's one of the definitions, right? Okay. And so then by definition, k is transient. Maybe I should say one of the definitions using tk. Okay. So now we can also think about the following case. So you can imagine the population here, they might go down to 0 and stay at 0, right? So they become extinct. Another way you can think about it, there might also be a chance for they to live forever, right? So that means like xn will always be greater than or equal to 1 for any time n. And this is also something which is a little bit interesting, that right, just coming from this statement here. So I'll just say so we call that yeah, I'll move this up a little bit. So each transient state can only be visited a finite number of times. Right? So this is just the definition of the transient, right? What this means is that it's just for any k. So okay, I'll just write out. I'll just continue here. So for any k, inside the non-negative, or just say positive integers, for any k in the positive integers, there exists a random time that's called n, such that we can think about such that xn here cannot take the value 1, 2, 3 all the way up to k for this n that is greater than this random time n, right? Because this is simply because 1, 2, 3 up to k, these are all just transient state. So we know the Markov chain can only visit each one of them finitely many number of times. So this means there exists some random time, and here it's not deterministic, such that okay, sorry, this should be true, yeah. Such that if after a long time, our Markov chain cannot visit any one of these states, right? Because it can only visit these states a finite number of times. So when n here is a random large number, so it won't be inside the set. So what this implies that right? So this implies there are two cases, right? Either right. So we have the first case, which is just going to be, let's say, in this case, that xn is equal to xn plus 1 is equal to xn plus 2, etc. Right? They're all just equal to 0. Right? So that's the first case, and or I'll just say either this or the second case, which is just the xn here, they go to infinity as little n goes to infinity. Right? Maybe I'll take a quick pause here. Switch the forward. Questions? So these are just simply, sure, question. Yeah.
Is this like similar to the idea of like there's just like positive recurrent and null recurrent, or is this or like a direct positive?
Let's see. I guess this is just maybe not really positive null recurrent because these are all transient states, right? Yeah.
I guess zero would be.
Yeah, zero. Yeah, zero in this case will be a recurrent, and it has to be a positive recurrent because it's just in its own communication class, right? So zero would be a positive recurrent, item. Well, I guess let's see. Sure. Is zero positive? Yeah, yeah. It's a little. Okay. Yeah. I see. I see. Yeah, yeah, that makes sense. Maybe, yeah, maybe it's not always positive recurrent. Yeah, yeah. Zero could also be yeah. Yeah. Let's see. Zero. I guess with that assumption, P0 is between 0 and 1. I just want to say. Okay, that's a good question. So whether zero can be no recurrent. Let's see. Yeah, this is something that we can think about. That's a good question. So over here, a great question to think about is over here we know that zero is recurrent, right? But so whether if zero would be a positive or no recurrent for this Markov chain, I guess it might depend on the sequence. Let's see. Okay. Well, we can think about this a little bit later. I want to get to a calculation for and okay, this is a good question. Okay. Yes. Second point. Oh, sure. I mean, it just means the number of, yeah, the value of x, yes. The number of individuals will go to infinity. Right. So you can think about the first case when the population just the population goes extinct, right? So there will be no individual in the population. The second one is like they blow up, they become infinity. Right, they cannot happen at the same time. Yeah, it represents two different cases. Yes, and there's also some meaning, right? So I mean, I'll just say this, all right? So you can think about this way. One is like, if we ask for the infinite survival of the population, that means they don't go extinct. That means the number of individuals in the population, they have to blow up to infinity. Right? So there's no way, for example, let's say let's ask the population to live forever, but then we want to upper bound the population number by, let's say, 1 billion. That doesn't really happen. That cannot happen. Right? So you either go extinct or the population number blows up to infinity and then you get infinite survival. So you cannot really get infinite survival by just looking at, a fixed amount of individuals in the population. Right? So this is this is an interesting observation. Oh, let's see. Thank you. I did. Yeah, thanks. Okay. Okay, so next maybe okay, there's one calculation I want to do, and so there are some like a natural set of questions that for example, we can ask. So maybe I'll just say this. Like we can ask like, what is the expected number of individuals at a given time or given level n, right? And then we can also ask like, what is the probability that the population will go extinct, which is this case. And we can also ask like, if the population will go extinct, and then we can say like when does that happen, right, in general. So I think for the next couple of lectures, we're just going to focus on the question that What's the probability that the population will go extinct? This is going to be our guiding question, right? What is the probability that the population goes? So this corresponds to the first case where, you know, after some random large capital N, all the number of individuals in the population will just all be 0, right? So yeah, I guess, yeah, you can think about that. Yeah, that would be like the exit distribution that we go to 0. Yes. Okay. Right. So it's essentially what's the probability, you know, the first case happens opposed to the second case. Right. So let's look at a case where this is easy to compute, and then we'll just look at it. And then, so first, so let mu, let's use this to know the expectation of our offspring distribution z, right? So it's a z and I, where the ni are ignored, right? So this is called, this is it. This is the mean, or the expected number, mean number of offspring from an individual. Right? And of course, then we can compute this mu, right? So mu, by definition, this can be computed. So how do we do it? We just go, I go from 1 to infinity of I times the probability that z is equal to I, right? And this is just going to be the summation I goes from 1 to infinity of I times pi. Right? So this is just going to be, in general, mu is just given by this. And now we can look at the following. So if what is the expectation of xn plus 1, given that xn is k, right? So this is something that is easier to compute than the transition probability. Right? Well, if we were given that xn is k, then the formula in the first board can be easily applied, right? In the blue circle there, right? So this is just going to be the well, it's just going to be, I'll just write down. It's just going to be k times mu, right? Because over here we're summing just only k many of these IID random variable z's, and each one of them will have expectation mu. And then in this case here, this expectation will just be k mu, right? From the blue circle, right? So this is we sum k many IID z's. Right? Each one has expectation mu. Okay. So now with this, we can do the following computation. So it's in general for any given initial distribution. So x0 could be anything. And then we can ask, what is the expectation of xn? So we're going to do a quick computation for this. Right. First of all, by definition, this is just summation. I goes from 1 to infinity of I times the probability that xn here is equal to I. Right? Okay, maybe sorry, I'll change the notation a little bit. I want to be consistent with the notes, so I'll change it to k. Right? So this is by definition. Okay. So now this is summation k goes from 1 to infinity of k, and in this step here, I want to apply the law of total probability. So we're going to summation over I goes from 1 to infinity. Okay, oh, it's 0 actually. I goes from 0 to infinity, and the probability p that this will going to be xn is equal to k, given that sorry, not given, condition on the xn minus, not condition, intersecting. At the previous step, we are at I. Right? So this is just the law of total probability. And of course, naturally next, I want to rewrite this as a conditional probability. So this is going to be summation k goes from 1 to infinity. And we would also have a k, I goes from 0 to infinity. And then let's move the k here. And let's rewrite this as probability that xn is equal to k, given xn minus 1 is equal to I, multiplied by the probability p that xn minus 1 is I. This is by the definition of the conditional probability. Okay, so continuing from there. Now let's switch the order of the sum. So we have summation I goes from 0 to infinity. Summation k goes from 1 to infinity. And then we have k. And then we have the probability p that xn is k, given xn minus 1 is I. And then times the probability p that xn minus 1 is I. So now what we can do is we can just look at this sum here. Right, so what is the sum here inside the bracket? By definition, it's something we computed previously. It's an expectation, right? Right. So it's something that we computed up there, right? It's, what is this expectation? It's a conditional expectation, right? It's just, by definition, it's the expectation of xn given xn minus 1 is I, right? From the, just really just by definition. And then multiply, and then we're going to multiply the probability p that xn minus 1 is I. Right? Okay. So now recall that what this is I goes from 0 to infinity, right? So just over here, this is I times mu, right? So well, let me write mu in the beginning here, mu. Okay, I'll just write this way. Right? So this is I times mu times the probability that xn minus 1 is I. Right? And again, I just want to say that this is just, again, following from the from orange stuff. Okay. And, okay, well, maybe I'll just write it here. So, and now from here, we can factor out the mu. We can bring the mu to the outside of the sum. And what is the sum here? Can you guys recognize? Again, it's expectation. Right? It's the expectation of what? Okay. It's just the definition of the expectation, right? It's the expectation of xn minus 1. So maybe I'll take a little bit of pause. Yeah. And then I'll let you guys think about this, this computation. So in the beginning, we computed this conditional expectation. And then we somehow derived a formula. So let me rewrite it again. So we derived that the expectation of xn is equal to mu times the expectation of xn minus 1, right? So that's what the calculation so far that we have done, right? Any questions about the computation? Right? And of course, the steps between these are going from the sum to the expectation. There isn't just any math, they're just definition. By the definition of expectation, there's not much trick. And of course, here we can apply this formula inductively, right? So we can apply the same idea to the expectation of xn minus 1. So this term is going to be mu. So this is going to be mu, and then this is mu expectation of xn minus 2. right? If we just apply this formula inductively, then in the end, we're going to get to something, right? So this is just going to be, I think it would be mu to the n times the expectation of x0. Right? So this gives us this inductive, this formula here. So in general, the expectation of the of xn is equal to mu to the n times the expectation of x0. Maybe how much? 5 minutes. Okay, that's good. Let's see. So I'll just move to the middle board, and I'll. Okay. Where should I erase? Okay. Okay, I'll go to the first board. Any questions so far about the computation? Okay. And so in this case, now this is going to be the simple case, right? So assume that let's say in this case mu is strictly less than 1. So this is somewhat a really natural assumption. This means the expected number of offspring produced by each individual is strictly less than 1. Right? And as you can guess, what would happen to the population? That they would go extinct, right? I mean, on average, each one of them will produce less than 1 offspring. Right? So this is like really the simple case, right? And then the expectation of xn, which is equal to mu to the n, with expectation of x0, this goes to 0, right? And this actually goes to 0 exponentially fast. Right? And okay. Right. So in this case, maybe I'll just write this. So let's say, what's the probability that xn is always going to be greater than or equal to 1, right? So we know that this probability here is, of course, bounded by the expectation of xn, right? So you can think about this as a Markov inequality. Right, a Markov, or you can just think about naturally, if I have a random variable, I mean, the probability that is greater than or equal to 1 just has to be less than the expectation of this probability, right? Because it's non-negative, it takes value in the non-negative integers, right? So this just has to be less than this expectation, and this is going to be less than or equal to mu to the n times some fixed constant, this thing, right? And well, in this case, we know that, so then this implies the sum as n goes from 1 to infinity, the probability p of xn is greater than or equal to 1. This is infinite, right? Because this is bounded by a geometric series. Right? Because this is summable in n, so that this term here is summable in n. So if we have a sequence of events such that their probability sum up to the sum is finite, what kind of theorem that we can apply? There should be like a well-known theorem, maybe from your previous probability class or analysis class, I guess. It's called the Birol-Cantelli lemma, right? Do you guys know the? Okay, maybe not from this. Okay, then okay, ignore this. So I'll just say this. Okay, so you can imagine that this probability here decays really fast as n goes to infinity, right? So the result I want to say is the probability that the population goes extinct goes this is 1 if mu is strictly less than 1, right? And it's also somewhat of a natural thing to think if the expected number of individuals that they reproduce is strictly less than 1, of course, the population would go extinct almost, right? Okay. And then in the next couple of lectures, we're going to look at what if the mu is equal to 1, or mu is strictly less greater than 1. Right? So we're going to look at the what if I don't know, what is the probability that the population goes extinct. So this is going to be the guideline for the next couple of lectures, right? So in the simple case here, mu is strict less than 1, we have shown that this extinction probability is actually 1. Right? And you can think about the reason this is true is because, at each time n, there's at least one individual, right? This probably decays exponentially, right? So this just means the complement of this, the probability that x is equal to 0 grows exponentially fast to 1 is 1 minus this number. Right? Okay. Okay, and that's it for today.